The antibiotics we know today don't work anymore. That's why superbugs, bacteria resistant to modern antibiotics, kill some 700,000 people each year, an equivalent to the population of Detroit, Montenegro, or one of Siberia's largest cities, Tumen.
Sounding the alarm about nightmare superbugs.
There are no new antibiotics in the pipeline.
It is the end of the road for antibiotics unless we act urgently.
There is hope for mankind, though. These little amphipoda crustaceans from Lake Baikal might be the answer. In 2013, biochemists from Irkutsk in Siberia decided to find out how these Baikal amphipoda protect themselves from infection, given that their main source of food is dead organisms found on the bottom of the lake. Turns out there are actinobacteria living on the crustaceans that produce exactly what researchers worldwide have been looking for: new antibiotics.
Antibiotics that are produced in the Baikal crustaceans and Baikal organisms and bacteria are extremely effective.
It was Alexander Fleming, the man who discovered the first antibiotic, penicillin, who warned how adaptable the bacteria was. He urged people to use antibiotics only on prescription and to stick to treatment. Otherwise, the pathogenic bacteria becomes immune instead of dying. So when penicillin's mass production started in 1943, it took just 4 years for the first bacteria immune to the antibiotic to be discovered in 1947. The golden age of antibiotics came to an end in the 80s when scientists stopped discovering new active compounds. So to save hundreds of thousands of people dying from superbugs, the world needs a wealthy source of previously unknown chemical compounds, one that could last for years to come. But let's go back to the amphipoda crustaceans. Why are they unique? Well, first of all, the actinobacteria that live in them are very diverse. Your average freshwater basin may be home to 1, sometimes 2 amphipoda species, while more than 350 amphipoda have been spotted and documented in Lake Baikal alone. Through millions of years of evolution, the Baikal amphipoda managed to occupy all kinds of eco-niches, and scientists believe there are actually more than 1,000 of different species living in the world's deepest lake. Also, Baikal amphipoda are great at adapting to extreme conditions. Baikal's average temperature during the year rarely goes above 4 degrees centigrade. That's pretty cold. Food sources in Baikal are scarce. Deep water crustaceans dine on whatever falls onto the bottom of the lake, dead organisms most often, a fine menu of detritus. And the antibiotics that the amphipoda produce help them to safely consume even infected organic matter. Back in the 70s, this ability to adapt by the Baikal amphipoda led to some unexpected consequences. A particularly ancient species of the Baikal amphipoda, the Gmelinoides fasciatus, was introduced into the waters of Volga to feed the local fish. Milder temperatures and conditions allowed the amphipoda to spread all the way into Lake Ladoga and Lake Onega, and then out into the rivers of western Russia within just a few decades. This diversity and ability to adapt to extreme conditions of the Baikal amphipoda and actinobacteria resulted in the potential discovery of tens of thousands new antibiotics. It's the jackpot scientists were waiting for.
We already have working materials. We understand what we're working with. We know where to look and where not to look. We know which types of crustaceans to study and which not to. We have conducted a huge preliminary screening concerning thousands of actinobacteria.
In just 5 years, scientists from the Baikal Research Center and the Irkutsk State University discovered 15 new antibiotics, currently under the name Baikalomycin. It's a years-long journey for a crustacean to turn into an antibiotic. Scientists have 2 main spots where they source the crustaceans. The small town of Большие Коты on Baikal's shore. This is where deep-water crustaceans are caught. And the town of Listvyanka, near the non-freezing riverhead of Angara. Nets are used here to catch coastal crustaceans. Crustacean mush then finds its way onto Petri dishes to culture antibiotics producers. The dishes are placed into warm, some 28 to 30 degrees centigrade thermostats to cultivate bacteria. Then strains are selected from what has grown, followed by a screening that defines which bacteria the substance is most active against.
Around 80% of the actinobacteria we pick out is active against at least one strain of microorganisms.
The most active substance is cultivated in larger quantities and gets turned into pure substance.
And this is the result of our work. This sample contains 150 natural compounds, but also 2 new antibiotics. I don't see any technical issues, and I think it's possible to create a new antibiotic every month. If all goes to plan, this could be achieved in 8 to 10 years.
And here's a fun fact before we go. Remember how we said that deep water crustaceans eat anything that falls onto the bottom of the lake? Well, local police stopped searching for the drowned in 10 days, because that's exactly how long it takes for the crustaceans to devour an entire human body.